is time for us to take everything we have learned about calculus and tie it all back to option Greeks. But before we proceed, a word of warning. Much of the math in options, and finance more generally, is based on approximations. So if you are a math-inclined person, know that here be dragons. And let's start off by taking a closer look at one of these dragons, which is the difference between price and value. The price of something refers to the amount you need to pay to purchase it, or the amount you could receive if you sold it. In other words, price is determined by the market. Value, on the other hand, is the output of a model. In the context of options, this would mean an option pricing model. However, models are constructed based on assumptions, and they often rely on subjective inputs. As option Greeks are derived from an option pricing model, they too are influenced by assumptions and subjective inputs. The end result is that option Greeks are approximations. Now that we have been sufficiently warned, let's begin. With options, we have one dependent variable, the value of our option, which is typically represented with a C for a call and a P for a put, with uppercase meaning American style exercise and lowercase meaning European style exercise, although this standard is not universally followed, but I will adhere to it. As for independent variables, we have 6 of those. But the strike price is usually fixed, so we aren't going to look at any option Greeks to do with that, as they are not used for vanilla options like you would see traded on an exchange. That gives us 5 independent variables of interest, which in turn gives us 5 first-order Greeks. As you have surely guessed by now, these are just the first partial derivative of the option's value with respect to the factor they measure. Let's look at each in turn, starting with the one that is slightly different from the rest, theta. I say that theta is not like the rest, as it is the negative of the partial derivative. That is because theta is the change in the value of an option as time to expiration decreases, which is the natural flow of time. If it were the positive of the partial derivative, then it would be measuring the slope as time to expiration increases. So to reverse it and get the partial derivative of the value of the option as time to expiration decreases, we simply take the negative of the partial derivative. The other 4, delta, Vega, rho, and phi, are just your standard partial derivatives. Delta is the change in an option's value given a change in the price of the underlying. This one has multiple interpretations, as alluded to in the introduction to this course, and we will go over those in a future lesson where we do a deep dive into delta. Delta is probably the most watched option Greek and is used, as the name suggests, in delta hedging. But delta is also important, at least in the context of the math we covered, in that it leads us to the most watched second-order option Greek, gamma. And if delta is the slope of the option's value with respect to the price of the underlying, that would mean that gamma is the convexity of the option's value with respect to the price of the underlying. And we can see that is true, as gamma is positive and the value of an option exhibits positive convexity along the price axis. In fact, it is this convexity that makes options attractive to some, allowing for profit and loss scenarios that otherwise would not be possible. Many option traders view purchasing an option, especially ones expiring in the short term, as buying gamma, or in other words, purchasing positive convexity. We will examine why that is when we look more closely into gamma. Next, we have Vega, which is the partial derivative of the option's value with respect to a change in expected volatility. Vega is a little different from the way we covered partial derivatives when looking through the lens of calculus, as volatility is neither on the x-axis nor the y-axis, but affects the value of the option nonetheless. Conceptually, it is still the same thing, but this shows that partial derivatives need not be on one of the axes. Another difference of Vega compared to the others is that it is a partial derivative with respect to a parameter, not a variable. This means that expected volatility is not known, nor is it observable, while the other inputs to the option pricing model are either known or are observable in the market. Vega also leads us to a second-order Greek which is somewhat popular, Volga. Volga is often referred to as Vega convexity, flat out stating that the second partial derivative of the option's value with respect to volatility has to do with convexity. Volga is not traditionally considered to be part of the standard set of option Greeks, but is used in delta hedging and comes into play when trading the volatility of volatility, which we will see in a later lesson. Rho, which is the change in an option's value for a change in interest rates, is similar to Vega in that interest rates affect option prices but are not on one of the axes. Interest rates don't have a huge effect on option values, but can cause some counterintuitive results, such as the value of a European exercise option trading for below its intrinsic value. And then there is the inverse to interest rates, which is dividends. This gives us phi, which we can see visually is the inverse to rho. Phi is not used much and is even sometimes referred to as rho 2 or dividend rho. And given its inverse relationship with rho, one can easily infer what the approximate impact to an option's value would be for a change in dividends if one already knows rho. To further demonstrate that option Greeks are just the partial derivatives of the option's value with respect to each factor, to create the plots for all of these lessons, I created an option pricing library that calculates the Greeks by taking the partial derivative of a factor. Here is the code used to calculate delta. The grad function takes the partial derivative of the function it is applied to. In this case, vx.models.black-scholes.price, with respect to the variable specified, which for this code is spots, which is the variable in position 3. In programming, numbering almost always starts at 0. If we wanted theta instead, we could just change the variable to be with respect to expiries instead of spots and put a negative sign in front of the whole thing. And if we wanted to calculate the theta for an American exercise option, then we would change the function referenced by grad to Bjerk's and Stensland 2002, or another option pricing model capable of valuing American exercise options. While this library may not be the fastest, it does allow us to visualize any option Greek we can think of, whether part of the standard set or not. It also allows us to calculate option Greeks for option pricing models outside of the typical Black-Scholes-Merton framework. Now that we are satisfied that option Greeks are nothing more than partial derivatives, let's look at some properties of option Greeks that come from calculus. We'll start off by looking at mixed option Greeks, which come from mixed partial derivatives. While they're not part of the standard set of option Greeks, mixed option Greeks can come in handy when analyzing an options position, especially one that involves delta hedging. For example, there is charm, which is both the change in the delta for a change in time and the change in theta for a change in the price of the underlying. Charm is a second-order mixed Greek and is sometimes referred to as delta bleed, as it measures the time decay of delta. This one becomes important when delta hedging because delta's time decay intensifies as the options near expiry, and so will impact a delta hedging strategy when held close to expiry. Another second-order mixed Greek that will be important for delta hedging is Vanna, which can be interpreted as a change in delta for a change in volatility, or a change in Vega for a change in the price of the underlying. As Vanna measures changes in both delta and Vega, it is used to adjust the delta hedging strategy for changes in volatility. It is also used in Vega hedging to adjust the Vega hedging strategy for changes in the price of the underlying. There are also third-order mixed option Greeks, an example of which is Zomma, which is often viewed as a change in gamma for a change in volatility, and so is sometimes referred to as d gamma d vol. Zomma can be useful when delta hedging, especially when determining the effects of large jumps in the price of the underlying on gamma, and hence on the effectiveness of a hedging strategy. For now, the point is that there are plenty of mixed option Greeks, many of which are useful in different circumstances, but some of which are useful when delta hedging. Adding the options P&L to the color scheme from the previous video, we get the full color scheme that will be used in this course. However, instead of calling them by the derivative, options traders typically refer to them as the order of the option Greek. So instead of first derivative, they would say first order Greek. And this color scheme will help us to identify which order of Greek we are looking at. And as mentioned in the previous video, the gradient is meant to make it easier to see detail, as solid colors can sometimes obscure detail in three-dimensional plots. And there are no mixed first-order Greeks, because a mixed Greek is when you take the partial derivative with respect to one variable and then another, so a minimum of 2 times. Another convention that I will follow is to have standard option attributes, meaning that unless otherwise specified, all options will be European exercise, have a strike price of $100, an expiration of 90 days, and will be priced assuming an interest rate of 5%, a dividend yield of 2%, and a volatility of 32%, and will be priced using the Black-Scholes-Merton option pricing model. You may be wondering why I chose 32% volatility. Well, what is volatility? It is the standard deviation of continuously compounded annual returns on the underlying. Since the normal distribution used in Black-Scholes-Merton assumes that 68% of all occurrences will fall within plus or minus 1 standard deviation, many consider that to be a typical move in the underlying. And we can convert an annualized volatility into a daily volatility by dividing by the square root of the number of trading days in a year, which is typically just shy of 256. Since the square root of 256 is 16, then a rough approximation to a typical daily move is to just divide volatility by 16. This is known as the rule of 16. At times, I will want to illustrate properties of options by increasing or decreasing the volatility. For that, I will use 48% and 16% volatility respectively. So I start with a volatility that equates to a typical daily move of about plus or minus 2%. And then I will shock that to volatilities that equate to typical daily moves of plus or minus 3% when increasing volatility and plus or minus 1% when decreasing volatility. Using these increments is meant to give us some intuition on what the change in volatility implies for expected moves in the underlying. Now let's take a look at the Greeks of a multiple option position, which is where the sum rule comes into play. If you were to get into an option position consisting of multiple options, what would be the Greeks of that option position? First, you have to consider whether you are long or short an option. If you are long an option, then you add the Greeks of that option. Whereas if you are short an option, then you subtract the Greeks of that option. So if you were to enter into a bull call spread, then you would be long a call with a lower strike and short a call with a higher strike, both with the same time to expiration. The delta of this position would then be the delta of the long call minus the delta of the short call. Well, that is an interesting pattern. Is it what you would have expected? Thinking it over, it does start to make sense. First, the delta of the strategy would always be positive or zero, as the profit loss is always either upward sloping or flat. Second, the profit loss is flat or nearly flat when the underlying is below the lower strike or above the higher strike. So the delta would be close to zero in those regions. But the delta should be higher, reaching a height of 1 when close to expiration and in between the strikes, given that the profit loss increases at most at a 1-to-1 rate with the underlying in between the strikes. Now that we have seen the delta, let's take a look at the gamma for this option strategy. The plot of gamma appears to be more as expected. Positive gamma near the long option strike and negative gamma near the short option strike. Long options always have positive gamma, and short options always have negative gamma. Meanwhile, theta is the opposite. One of the goals of this course is to help you think of options in terms of their Greeks. Once you do, you'll end up thinking of buying options as buying gamma and paying theta to get it. And when you think of it that way, it becomes intuitive that gamma and theta are inverses. We will touch on this more in a later lesson. Moving on to Vega, we would expect the long option to exhibit positive Vega and the short option to exhibit negative Vega. Let's see if that is the case. And this one is also as expected. In another playlist, we will go over the characteristics of different option strategies and their Greeks, so this has just been a taste to demonstrate the sum rule and its application to option Greeks. One very important caveat to using the sum rule to add and subtract the option Greeks of a multiple option position is that the volatility of one strike will not always move in tandem with the volatility of another strike, and changes in volatility can impact the way other Greeks behave. So it is important to keep in mind the option Greeks of the individual options and to be cognizant of the volatility dynamics when combining their Greeks. Now that we are armed with a deeper understanding of option Greeks and the math behind them, let's really dig in and understand option Greeks at a deeper level. In the next lesson, we will cover put-call parity and how it relates to option Greeks. I would like to give a special thanks to those who support this channel on Patreon, especially for the comments they provided on early versions of this video.